Good afternoon, good morning, everyone. Good evening. So it's a pleasure to introduce Dapeng Mu, who is a postdoc here in Campinas, currently spending a period at the University of Edinburgh. And he's talking about stable pairs for rank 2 sheaves on projective space. Dapeng, please go ahead.
Okay, well, thank you. So good morning, good afternoon, good evening, everybody. So I'm going to talk about stable pairs for rank 2 sheaves on the projective space. So this is a joint work with Professor Marcus Jardim. We're about to finish. Let's see. So how should I turn it? Okay. So this is the outline of the talk, and you see there are many items, like 7. So I think it's too much for 1 hour. So I will skip some of the details. So maybe I'll just keep the slides, but I'll skip some details. So if you're interested, then maybe we can discuss afterwards. So let me briefly go through the outline. So first is about the motivation of this work. And so we would like to generalize the Serre correspondence into a flat family. And the tool we used is this coherent pairs and their stability conditions. And then we're going to see the wall crossings. And then I will show 3 of our main results. So finally, if I still have some time, I will show 2 more applications. So this is basically the outline. Let me start with the first one, the motivation. So let me start from the Serre correspondence. So this is the motivation, and then I will start with Hartshorne's theorem about the Serre correspondence on P3. So the theorem says there's a one-to-one correspondence between the following 2 pairs. The first pair is consists of a rank 2 vector bundle. I call it E, and with a section. So we also require that the 0 locus of the section has codimension 2. So the 0 locus is a curve. The second pair consists of a locally complete intersection curve with some extension class. So I think, simply speaking, I can explain in the following way. So let's look at this project sequence. So suppose the co-kernel of the section is torsion-free. So in this case, it's rank 1 torsion-free, so then it has to be a twisted ideal sheaf. So if I want to go from one hand side to the other, so for instance, if I want to go from a sheaf with a section to a curve, then the curve is basically the 0 locus of the section. And then if I want to go conversely, I start from a curve, then the sheaf would be the extension of the ideal with O. So this is basically the correspondence. Right, so our goal is to generalize this set theoretically correspondence into flat families, so that we hope that both families have good moduli spaces. So you will see in the first row, so the expected correspondence would be a flat family of rank 2 sheaves, and we have a flat family of curves. So see, I put semistable in parentheses, meaning so the first idea of this flat family of sheaves that has a good moduli space would be to consider semistable sheaves. So I put semistable in parentheses. So the expected moduli spaces would be the moduli of Gieseker semistable sheaves on the sheaf side and the Hilbert scheme on the curve side. But unfortunately, so this doesn't work directly. And so actually we have counterexamples for both directions. So for instance, from the curve side to the sheaf side. So the trouble is we may start from a curve, and with a corresponding sheaf, the extension is stable, Gieseker stable. But as the curve is deformed into some planar curve, then the Hartshorne's criterion says the extension is no longer mu stable. So it won't be Gieseker stable either. On the other side, so we go from the sheaf side to the curve side, then the trouble would be we start from a rank 2 sheaf with a section, then this pair doesn't always correspond to a curve. Meaning we write down the short exact sequence, the co-kernel of the section may not be the ideal sheaf of some curve, so it can contain some torsion. So this would be the trouble. So in general, this correspondence doesn't work directly. So our solution was considering stable pairs, and then here's basically some motivations. So let me continue from the counterexample from the sheaf side to the curve side. So the setting is we're given a rank 2 torsion-free sheaf and a section. So we hope that this pair corresponds to a curve. So this means we hope the co-kernel of the section S. So in the sequence, okay, so let me use this tool. Okay, so in this Schroeder sequence, we hope this co-kernel is torsion-free. So torsion-free rank 1 means it's ideal of some curve with a twist. But this is not always true. So okay, I should go back to this mouse. Okay. So let me clarify some notations. So suppose a pair, a sheaf with a section, it corresponds to a curve, meaning the co-kernel of the section is an ideal of y. Then I will say this pair corresponds to the curve y. Or conversely, this curve y corresponds to the pair E, S. So this is going to be the notation. And then we give it a formal name. So we call such a pair saturated if this pair corresponds to a curve. Okay, so here the issue is that a pair may not be saturated, or it may not correspond to a curve. And then this is our solution. So further, so suppose we have an unsaturated pair. So meaning the pair, the co-kernel of the pair Q is not torsion-free. So we consider the natural the torsion subsheaf T, the maximum torsion subsheaf. So this Q multiplied by T would be torsion-free. We consider composition from E to Q and to Q quotient by T. And then we let L to be the kernel of this composition, so as shown in this diagram. So this one naturally gives a subpair. So I will introduce the notation of a subpair in the next few slides. So the idea is, so once we have an unsaturated pair, and then we'll have a subpair. So the subpair always comes with an unsaturated pair. So this is the idea. Okay, so this is our motivation using stable pairs. So for instance, if a pair does not correspond to a curve, so there's so here comes naturally a subpair. So we want to rule out such a bad pair by saying the subpair destabilizes this unsaturated pair. So that motivates the consideration of stable pairs. Okay, so this is about the motivation. Do you have any questions before I move on? Okay, so then let me introduce briefly these coherent pairs. So for coherent pairs, I think we can work on some more general algebraic scheme, and I will call it X. So we say coherent pair E, S, a pair on X. So if it consists of a coherent sheaf E and a section of the sheaf S, and then we can talk about the subpair. I think the next few definitions are due to Hilbert. So we say a pair F, S1, a sheaf with a section, is a subpair of a given pair if the sheaf F is a subsheaf of the sheaf E, and moreover the section S factor through the section of the subpair. So this means the following diagram commutes. So we do not only have a subsheaf, but the section has to factor through the section of the subpair. So it's more restricted than a subsheaf. And then we can also talk about stability conditions. So here, let me restrict X to be a smooth projective variety over the complex number field. So again, I think the definitions were due to Hilbert. So in this setting, we require so it's one more parameter. So it's not a single stability condition. So it's a family. It depends on a parameter. I will call this parameter delta. So delta is a polynomial with rational coefficient with a positive leading coefficient. So this is the parameter we're going to use for stability conditions. Okay, so so you will see the setting is very similar to stability condition of Gieseker stability of a sheaf. So firstly, we use the Hilbert polynomial. we define the Hilbert polynomial or reduced Hilbert polynomial for a pair. So this is defined as the usual Hilbert polynomial plus this extra delta divided by the rank. So you'll see there's a coefficient epsilon with delta. So this means when your section, this S, okay, let's see, okay. So here we have a section. So in the special case that this section is 0, then we don't put a delta there. So now the pair is reduced to a usual sheaf. But if this section is not 0, then we'll need to put this extra delta in the numerator. So we say this epsilon is equal to 1 if S is not 0, otherwise it's 0, and then it's reduced, the pair is reduced to a sheaf. We say a pair is semi-stable or stable with respect to some delta if for any subpair the reduced Hilbert polynomial of the sub is less than or equal to the Hilbert polynomial of the pair E comma S. This is very similar to the case of a sheaf. Okay, and the next result says, so similar to the case of sheaves, so the Hutton-Seaman filtrations and Jordan-Holder filtrations exist. I think maybe most of you know about this, so maybe I don't want to talk more in detail. So Hutton-Seaman filtrations, Jordan-Holder filtrations exist. And then I will talk about the moduli spaces. I think the following few results were due to these authors. I think they work on some higher dimensional varieties and in the more general context of a coherent systems. Okay, so I will start with a flat family of pairs. So before the moduli functor, we have to clarify what is meant by a flat family. So in this situation, a flat family of coherent pairs over scheme, it basically means the underlying sheaf, this family of sheaves in this pair is flat. So in the more general setting, when we have a coherent system, then you will see some more complicated definition of flat family, but this is a special case. So in our case, a flat family of pairs means that the underlying sheaf is a flat family. Okay, and then we can talk about the moduli functor, which is I think it's the natural one from scheme to set. We assign to every scheme a flat family of pairs such that when restricted to fibers, they are delta semi-stable pairs for some fixed delta. And then this functor is co-represented by some projective scheme, meaning it has a coarse moduli, and then the stable locus is a fine moduli. And this is exactly the same with the case for sheaves. So maybe let me mention the set of all coherent pairs on X form an abelian category. So we have a abelian category. Okay, so then we can talk about the derived functors. Well, still I will just state some basic results, but I will not go into the details. So in the abelian category of coherent pairs, so we can define injective objects. We can define some higher direct functors of the home functor. So it makes sense that for any two pairs, we can talk about the extension classes. So this is well defined. And I think the last result I want to say about the moduli space is the tangent obstruction theory. And then you will see the expression is almost the same with the case for sheaves. So at any point in the moduli of semi-stable pairs, so say the point corresponds to a pair, I call it lambda. The tangent space at that point is ext1, the self-intersection of lambda with itself, and then the obstruction class is containing ext2. Very similar to the sheaf case. Okay, so let me move on to the wall crossings. So here, so as I mentioned, we have a family of stability conditions. We don't have a single stability. So the stability condition depends on a parameter delta. So as the delta varies, and then I think it's a natural phenomenon that we have wall crossings. So I think simply speaking, it means the following thing. So in many cases, it happens that a pair is stable for some delta, but is unstable for some different delta. So for example, so I will show in this diagram. So this axis is this QP axis, is this rational coefficient polynomial axis, and then we give the order by the Lex order. So it's an axis, and then it happens that for some pairs, so ES, this pair, okay, so it might be stable for some delta, and it might be unstable for some other delta. So when delta varies from, say, in this picture, when delta varies from the place where it's stable to the place that's unstable, so it makes sense that it will pass some critical point, like this, I denoted by W. So when delta is equal to W, then this pair is strictly semistable. So so this happens, and then we call such a W a wall or a critical point. Okay, so let me go back to the mouse. Okay. So I will use the following definition to define a wall. So we say a W, a polynomial in this axis is a wall, or I think sometimes people call it the critical value, if there exists strictly semistable pair when delta is equal to that value. So in the general situations, so we'll have the set of stable pairs are different on the two sides of a wall. So a wall is a place where the modular space is changed. Okay. Okay. So now I think I'm going to state I'm going to talk about the first main result. It's our picture for the rank 2 class, the wall crossing picture for rank 2 class. So you will see we do have a generalization of the Serre correspondence. And then for the rank 2 case, we have some specific geometric meaning, geometric interpretation of the moduli of pairs. Okay, I think from now on, I will restrict myself to P3. So although it works on some other funnel varieties or funnel Picard rank 1, but for simplicity, I will just work on P3. Okay, so the first result is in this picture, but I will explain little by little. So, so my point is our first main result is all contained in this picture, and I will explain from right to left. Okay. Okay. So firstly, I'm going to explain this collapsing wall, this delta empty set. So let me go back to the previous slide. So I'm going to first explain this wall, and then I will move from right to left. So I'm going to explain this one secondly, and then this is the last one. Okay. Okay, great. So this is from this observation. So for every pair, E comma S, it always comes with a natural subpair. So say if this is the pair, and then there's always this natural subpair. So you just consider O to be the subsheaf. And then this identity, of course, this section factor through the identity of O. So we always have a subpair for any pair. And then, so for this one, we can compute the wall, the corresponding wall. So I will denote the corresponding wall by delta empty set. We'll see why do I use this empty set later, very soon. So by saying the wall for this pair, I mean the solution to this equation, right? So the wall is when your subpair and your pair have the same Hilbert polynomial. So it's an equation in delta, you solve for delta. So I'll call the solution delta epsilon, the delta empty set. Okay, so here's another observation just by some direct computation. If your delta is larger than the solution to this equation, and then the polynomial of the subpair will be larger than the polynomial of this pair, E comma S. So this implies that the pair will be unstable. So this indicates the following diagram. So for any given pair, we have this collapsing wall. So what I just stated implies that when delta is larger than this point, so every pair is unstable. So this is saying the only interesting thing happens between 0 and this very last wall, this delta empty set. So we call it collapsing wall because after this point, everything will be killed and the modular space will be empty. Okay. The second wall was this saturated wall. So so recall that for every pair, so suppose this pair is unsaturated, meaning it does not correspond to a curve. So remember, we always have a subpair, so that comes with this pair naturally. And then I will denote by the corresponding wall delta L. So L is the destabilizing object. So we have a wall for this pair. So a direct computation shows that when delta is larger than this critical point, then this pair will be unstable. So this motivates our definition of, I think we call it like a torsion free wall in our paper. So we define this delta T to be the maximum wall in between 0 and the delta empty set. Or in other words, this is the second largest wall. So there was a theorem in the closed paper, so I mentioned in the beginning. So there exists a maximum wall, so it makes sense to define the maximum or the minimum. So this let delta T be the second largest wall, which is the one smaller than this collapsing wall. And then any delta stable pair for delta lying in this chamber from delta T to delta empty set will be saturated. So this, okay, so I think up to this point, I can explain this bit. After this collapsing wall, I have a second largest one. So we also know that every stable pair in this chamber will be saturated, because otherwise you have a wall that will be lying in between this delta T and delta empty set, which contradicts with the maximality of delta T. So so moreover, we can construct a morphism from the moduli of pair to the Hilbert scheme. So so this morphism sends every pair to these co-kernels. In this case, the co-kernel is torsion free. So we are sending every pair to an ideal sheaf. So it induces a morphism from the modular pair to the Hilbert scheme. So the fibration, the fiber of this fibration is turned out to be the extension class, the proj of this extension class. Okay, so this is the second wall I want to explain, and then we have a third one, which is the smallest one. So this is from the following observation. So this fraction is the reduced Hilbert polynomial of a pair. And then when this delta is sufficiently small, it's very close to 0. So this is almost equal to the Hilbert polynomial of the sheaf. So this implies that when delta is very small, and then we can prove a delta stable pair has a Gieseker semistable underlying sheaf. So the underlying sheaf is Gieseker semistable. And then, okay, so therefore, we define delta 1 to be the minimum wall. So the first one that is larger than 0, and then also this exists. And then I think up to this point, I can complete the description of our first main result. So, okay, so I just introduced this torsion-free wall. So meaning in the very last chamber, every pair is saturated. So we have a fibration over the Hilbert scheme. And then let delta varies to the left, let delta vary to the left. And then when delta lands in the very first chamber here, so what we see is that the underlying sheaf is Gieseker semistable. So similarly, we have a morphism from the moduli of pairs to the moduli of Gieseker semistable sheaves. So the morphism is induced by this forgetful map. And then the fiber in this case is basically the class of all the sections. The section, so it's a proj of the global section of a sheaf E. Okay. So maybe let me mention in this chamber, I think this is the generalized Serre correspondence we want. So on one hand side, we do have a family of curves, but on the other side, we have a family of sheaves, but not necessarily Gieseker stables. There are some Gieseker unstable sheaves. So we have a relation between the Hilbert scheme and the moduli, the Gieseker moduli space, but they're not connected directly, but they are connected via a sequence of walls. So for instance, in this very last chamber, every pair is saturated, so we have curves everywhere, but not every sheaf is stable. So if you want that, you have a moduli of sheaves, so what you do is you cross walls from right to left. So every time you hit the wall, there will be some Gieseker stable sheaves added to your moduli. but on the other side, there will be some curves removed from the Hilbert scheme. So when you land in the very first chamber, so your moduli space of pairs all contain Gieseker semistable sheaves as underlying sheaves, but you lose some curves. So yes, I think this is like the second best we can do, because the optimum Y doesn't work in general. Okay, this is our first main result. Right, so let me move on to the second one. Okay. So for the second one, so we try to generalize a criterion by Hartshorne. So he had a criterion of stability of a vector bundle in terms of the corresponding sheaves. So we use wall crossings and we generalize his criterion. So let me start with describing curves at a wall. So I mentioned like every time we cross a wall from right to left, so we lose some curves from the Hilbert scheme, but we have some Gieseker semistable sheaves. So I'm going to describe so what types of curves are killed when we cross a wall. Okay. Right. So so we just saw that when delta lies in the very last chamber, so every delta stable pair will be saturated. So we have a fibration over the Hilbert scheme. Right, so I think I just explained this. So when deltas get smaller, so every time I cross a wall, we lose some saturated pairs. So equivalently, we lose some curves from the Hilbert scheme. Yeah, so this is the philosophy, like we cross wall from right to left. So we'll gradually lose some curves, but we'll have some Gieseker stable sheaves. And okay, so in the next slide, I will describe the curves killed at W at the wall when crossing W. So firstly, let me describe a wall. So since our case is quite special because E has rank 2, so your sub and quotient they both have rank 1. So rank 1 torsion free, and this means your sub object and the quotient they're both the twisted ideal sheaves. So I mean a wall is of the following form, where ideal of A and ideal of B are both ideal of some one-dimensional schemes, but not necessarily pure. It can be a curve with points, but they're both one-dimensional. Okay. So we figure out the following result. So suppose we cross W, we cross this wall from right to left as delta gets smaller. So curves Y that satisfies the following diagram, so I call this diagram star, will be removed. So I mean the curves corresponding to W satisfy the following diagram. So let me explain a bit what this diagram means, some notations. So for instance, this A is the same with the A here, it's a one-dimensional scheme. So this B0 is the zero-dimensional subscheme of B, the maximum zero-dimensional scheme of B. So this C is not the same with B. So so here you will see I have a section of ideal B twisted by L. So this one actually gives me a surface, a hypersurface S in P3 of degree L. So C is a curve contained in this surface S. So C is lying in S, but the degree of C is larger than the degree of B. So the degree of C, like simply speaking, the degree of C is L times by K larger than the degree of this B. So B1 is the one-dimensional component of B. So simply speaking, C is a curve in S in some hypersurface of degree L. L is this twist, but it has degree larger than the degree of B. It's some curve with larger degree. And simply speaking, so this Y, so this Y is the union of the three objects A, B0, and C, like scheme theoretically. And this A and C intersect in this many points. So S dot A1. A1 is the one-dimensional component of A, is a curve. So S is a surface. You intersect, you get a bunch of points. So the length of points is the number of intersections of A and C. So I wrote in parentheses scheme theoretically. So it happens that A and C are the the underlying, so the reduced scheme of A and C can be the same, but Y is the non-reduced one. So I also call it scheme theoretically union. So it contains the special case that Y is non-reduced. Okay, now I think I can introduce this criterion. So let me start with this correspondence. We have a pair E with a section, and correspondingly we have a curve. So which means we have this Sheaves sequence. So Harshon has a theorem, a criterion for slope stability of a vector bundle. So for rank 2 vector bundle, such that it corresponds to a curve Y. So this bundle is mu stable or semi-stable if and only if the following two items hold. So the first one is a positive C1. The second one is this curve cannot be contained in any surface of low degree. So this low degree, I mean this the sense of low or high is measured in terms of half of C1. So it cannot be contained in some low degree, which means the degree of less than a half of C1 of E. So using the wall crossing, we can generalize this criterion a bit, but I think we can only generalize it in one direction. And I will make a remark to say why the converse is not always true. So we have the following criterion. So this E, in this case, can be a torsion-free, not necessarily vector bundle. Torsion-free rank 2 sheaf. Suppose it corresponds to a curve Y. So the sheaf is Gieseker semi-stable if this Y doesn't fit into this diagram in the previous slide, this diagram star for any possible A and B. So so let me start with a sketch of the proof. Actually, the idea is pretty simple. So firstly, we have the correspondence. So this means this pair is unsaturated. So it lies in the Hilbert scheme chamber. So it's fibered over the Hilbert scheme. So secondly, it doesn't fit into diagram star, meaning every time we cross a wall, this pair will not be killed. So when as delta varies, and when it lands in the very first chamber, or in other words, when delta is very close to 0, so this pair is still delta stable, but in this case, we have E Gieseker semi-stable. So maybe let me just make a remark orally. So it looks like this proposition is kind of weak, but actually in reality, you will see there are not many candidates for A and B. So it's not, well, I think it's not very hard to check. I think in practice, there are not many possible A and B. You don't have to check a lot. So the next thing I want to say is the converse is not true. So this is because suppose we have a curve that satisfies this diagram star, and then it does not necessarily recover the wall. So actually, this diagram contains more curve than the curves killed by the wall, and then I will show you one example later. Yes, so I mean, we're still trying to figure out the sufficient and the necessary condition, but up to this point, we only have one direction. Okay. So this is the second main result, and then do you have any questions before I move on? Okay, let me move on to the third main result. So before that, let me show two examples to motivate this result. So in the next two results, I will show the complete wall crossing pictures. So the first one is the simplest example. I fixed the class to be -1, 1, 1. So these are the first, second, and third chain classes, and the rank is 2. So these numbers are chain classes. Okay, so so firstly, we have a description of Gieseker semi-stable sheaves of that class. So a sheaf of this class is Gieseker semi-stable if and only if E fits into the following Sheaves sequence. In other words, we know that E corresponds to a curve for any section if it exists. It corresponds to it corresponds to a curve. The curve is a line. This L is a line, ideal of L. So we also know that such a stable sheaf has the following resolution. And so this N is a 3x1 matrix. The entries are some linear sections of O1, and these three are linearly independent. So this is a description of Gieseker semi-stable sheaves. Okay, I think I didn't write here. So the moduli, well, I mean, this resolution tells us the moduli of Gieseker semistable sheaf is a P3, because E is one-to-one correspondence with the zero locus of K1, K2, K3. The E is one-to-one correspondence with the points in P3, so the moduli is a P3. So the second fact is there are no walls between 0 and the collapsing wall. So there are no walls between, there are no wall crossings. Okay, so this means that the Gieseker chamber coincides with the Hilbert scheme chamber. And what we have is we have these two fibrations. So the moduli of pairs for any delta in between 0 and the collapsing wall. The moduli of delta semistable pairs has two fibrations over the Hilbert scheme. So in this case, the Hilbert scheme is the Hilbert scheme of lines, which is Grossmanian twofold. And it also has a fibration over the Gieseker moduli, which is P3. And then, so moreover, you can compute that the fibers are P1 and P2. So these informations are given by the wall crossing, the fibration pictures. So moreover, we can figure out that this moduli space is actually this flag variety point in a line in P3. So these fibrations are the fibrations to this P or to this P1. Okay. Okay, I see. So this is an explanation of that why this moduli space is a flag variety. So I think due to the limited time, I will skip this part. So I'll skip this description, and then you can trust me. The moduli space in the middle, this moduli of pairs, is the flag variety. But I will skip the description why it is. So this is the first example, and actually we didn't see the wall crossing. So in this example, so this is the second one. So in this example, you actually see the wall crossings and some birational transformations for those components. So here I'm going to fix a class 0, 1, 0. C1 first string class is 0, and C2 is 1, C3 is 0. Let me start with describing the Gieseker moduli and then the Hilbert scheme. So in this example, we know both of the moduli spaces very well. Okay, I think I'll just state the result, but skip some proofs. So the moduli space of Gieseker semistable sheaves, in this case for this class, is a P5. So you can compute that there are no sections for E of class V. But when you twist everything by 1, when you twist the sheaf by 1, there are some sections. In this case, the sections are C5. So this fibration over the Gieseker moduli, the fibers are P4 in this case. So moreover, we also know that this moduli space, when delta is very 0, which means this moduli of pairs is fibered over the Gieseker moduli, is irreducible, and is fibered over this P5, the Gieseker moduli. The fibers are P4. So this is a description of the fiber Gieseker moduli. And then for the Hilbert scheme, okay. So firstly, I will need to say we no longer consider the wall crossings for the class V, but we have to twist V by 1. So we have to consider class V1, which is defined to be the class of this E twisted by 1. So the reason is otherwise, if you consider wall crossings for V, and then the fiber Gieseker moduli will be empty because there are no sections for E, but there are sections for E twisted by 1. So we consider wall crossings for V twisted by 1. So in order for the fiber Gieseker moduli to show up. Okay, so we fix this class E twisted by 1, and then I'm going to determine the corresponding curve. So the curve is determined by this Sherzak sequence, and then you can compute that the Hilbert polynomial of C is 2t plus 2, 2t plus 2. And then the fibers are this extension class. So finally, we have this description of this Hilbert scheme. So P is the 2t plus 2. So there are two components in this Hilbert scheme. The dimensions are 8 and 11. A general curve in these two components are two skew lines and a planar conic with an extra point. So the fibers over these two components, so the fiber is the extension class, are P1 and P2. So over P1 minus P2, so on H1 of H2, the fiber is a P1, but it jumps on the intersections. Okay, so, right. Okay, so we know that in this fiber Hilbert scheme, there are also two components, and the dimensions are 9 and 13, because you do base plus the fiber. Okay. So this is a complete wall crossing picture for this class, and then maybe let me explain from the top row to the bottom. So so firstly, we have this axis. We have this axis. So this is the QP axis, the polynomial axis. We are only interested in the wall crossings between 0 and the collapsing wall. And then by computations, there are only two walls in between. So we consider two wall crossings at these two walls. So let me cross the walls from right to left. So I will start from this the fiber Hilbert scheme. So these are the two components. So you will see, so here for this H2 component, I'm marking blue. So because our more general result is a generalization of the result in this line, in this row. I think maybe let me start with describing the wall crossings for this H2. So let's recall that H2 is a component parameterizing planar curves with some extra point, with one extra point. So we start from the fibered Hilbert scheme. So it's a fibration over this H2. So when crossing W0, so this component is blown down. So I will call the new component H2 prime. And then we cross W1, and then an open locus is removed from H2 prime. So when we land in the very first chamber, then H2, this H2 tilde is completely removed. So correspondingly, so this H1 tilde undergoes two contractions while crossing the wall. But I think here we just focus on the second one. I think the first one, so for instance, for the first blow down, the divisor in H1 tilde is the divisor, the exceptional divisor of the blowdown for H2 intersect H1. So correspondingly, we have a blowdown for H1 as well. In the this third row, so I wrote the curves removed. Actually, we have a more general result. We have a more general description for a general situation. So for this very specific example, so when crossing the first wall W0, the curves removed are this planar conic with a point contained in the same plane. When we cross the second wall, the curves removed are the planar conic with a point, but this point is no longer in the plane. The space is a space point. It's set free from the plane. But maybe let me mention this is the general situation. So every time, so when we cross wall from right to left, so a curve killed at the wall is So I mean for two consecutive walls, so the curve on the left hand side is the curve on the right hand side, but you set some of the component free from the plane or set it free from some hypersurfaces. This is the general pattern when you cross wall from right to left. So here's the simplest case. We set a point free from the plane to the space. Okay. So in the fourth row, so I also wrote down every time you cross a wall, so there will be some locus added. So when you cross W0, you have a locus L0, but this is not a component. So this is the place that your exceptional divisor is contracted to. And then when you cross the second wall, you have another locus added to this moduli, L1. So right. It actually contains a lot. Maybe let me explain this part. So here you see the arrow. I pointed to these two curves and I say E is unstable. So this means, so this is the criterion. So you have a sheaf that corresponds to either this curve or the other curve, then the curve is unstable. The sheaf is unstable. And right, so for the other one, I point to L1 and L0. So L1 and L0. So stable pairs there have stable underlying sheaves. Okay. Okay, so there are two more things. So up to W1, so when you cross W0 and W1, so up to this point, so this component H2 tilde is completely removed, but you have this H1, so part of it survived. So finally, your moduli space, this fiber Gieseker moduli, consists of these three parts, H1 double prime and L1 and L0. So firstly, every pair in this modular space has its sheaf as underlying, sorry, so I mean, in this modular, every pair in this modular space, the underlying sheaf is Gieseker stable, is Gieseker semistable. In this case, they're the same, but not every pair is saturated. So you will see only H1 double prime parameterized saturated pairs. But for the other two parts, L0 and L1, the pairs there are not saturated, so they don't correspond to curves. Okay, so this is a complete wall crossings. Next, I'm going to generalize the result for this component. Okay. Okay, so this is our third main result, some birational transformation for one component. Let me start with some settings. So this component marked in blue, so actually it parameterizes some planar sheaves, planar curves with some points. I will call this component HP. So sorry. So let me start with some more general settings. So I start with some rank 2 class on P3, and then I will determine the curves. So so the curve is given by the sequence. So in particular, I require the C1 to be positive. So correspondingly, I have a curve, and then I let P to be the Hilbert polynomial of such a curve. And then we look at the Hilbert scheme. So there's always this component or components that parameterizes planar curves union points. But I think in general, this HP might contain more than one component. But in our work, we only focus on the case that this component is irreducible. So in other words, we only consider the case that any curve with points can be deformed into a pure curve with some separated points. So we only consider this situation. So this HP component that parameterizes planar curves union points is irreducible. We only consider this case. Okay, so we know that for some delta in the very last chamber, we have the modular space of pair is fibered over the Hilbert scheme. So in particular, I denote by HP tilde to be the component lying over HP. HP, remember HP parameterizes planar curves union point. So I denote by HP tilde to be the component. In this case, is also irreducible in the modular pairs that's lying over HP. Okay, so sorry, there are still some settings before coming to the main result. I will need to say, so why do we study this component? Well, this is because, so we mentioned that the largest wall is the collapsing wall, but the second and the third largest wall, they correspond to this component, and this is one of the reasons. So I'm going to introduce a sequence of walls, Wi. So you'll see this is a definition. So something special is this Pi is no longer one-dimensional. So here they are zero-dimensional. And then these walls turn out to be the second largest one. So after the collapsing wall. So I should say before the collapsing wall. So here's the picture. So the largest one is the collapsing wall. The second and third largest wall are those W of i's. Okay. And then let me describe the curves killed at those Wi's. So previously we have the diagram. I call it diagram star. So this diagram star tells us the curves killed at Wi looks like the Ci, denoted by Ci. So Ci is a union of a planar curve Yi with some point in space, Pi, with some point Pi in space. So here I put in space in quote, well, because So maybe I don't want to say the very precise definition. So like PIs is in space scheme theoretically. So it can be a point, it can be an embedded point in a plane but pointing out of the plane. So I would just call such a point in space. Scheme theoretically in space, not contained in plane. Okay, so I think this is what I mentioned. So every time you cross the wall from right to left, so the curve you removed is the curve you just removed previously, but you set one of the points free from the plane. So this is a general pattern. So I give the notation. So I will denote by Zi to be the locus in the Hilbert scheme, parameterizing those Ci's. So Zi is actually a strata of HP. The union of Zi is this HP. Okay, so finally we come to this result. So when we cross the walls, as delta gets smaller, we have that this HP tilde undergoes a series of transformations. So for the first L-2 wall crossings, so here's the picture. So altogether we have a group of walls starting from W0 and stop at WL. So when you cross the first L-2 walls, this component HP tilde undergoes a flip. And then for the second last one, the WL-1, your component is a divisorial contraction or blow down. And then when you cross the very last wall, so there is going to be an open locus removed from this component. So I put a very small remark at the end of this slide. So we hope to use this result to prove this Gieseker moduli for rank 2 sheaf is connected. And then, so here I forgot to say. So here, so in particular, so if the moduli space we start with is connected, then we can prove that those wall crossings preserve the connectedness of the moduli space. And then, so actually we hope that when we cross all the other walls, it still preserve the connectedness, but those situations are harder than crossing those walls. Okay. Okay, the third main result. So finally, for the third main result, I'm going to make two remarks. So the first one is when I call a flip, this is not a flip in the rational geometry. So it just means that when I say from x to x prime is a flip, so then exists a y such that this phi plus and phi minus are both small contractions. We don't care about the canonical class. So this is what we mean by a flip. So secondly, so when you cross wi, so actually the locus that is contracted or removed is exactly this locus that's fiber over Zi. So remember, Zi parameterizes a planar curve with I space space points. Right. So finally, so since Zi is the strata of HP, so when we cross all those walls from W0 to WL, then this component HP will be completely removed. Okay, so so that is three main results. I guess maybe I still have like a few minutes, so let me just briefly say about two more applications. So we figured out the entire wall crossing picture for this class 038, and as you see, this is a bit more complicated than the previous one I showed you, the 010, and there are altogether like 1, 2, 3, 4 wall crossings. So you will see, maybe I'm going to emphasize two things. The first one is this component H1 tilde. So this is this HP tilde I just showed. So when we cross W0, W1, and W2, so this component undergoes a flip, blow down, and removal of an open locus. And then up to this point, when we cross W2, so this component is completely removed. So that's the first thing. Which matches the proposition I just showed. The second one is there's an actual wall, W3, which is not contained in this group of wall I just introduced. So in this example, for this specific class, when crossing W3, the other component undergoes a flip, and then the corresponding curves killed are described in this picture. So it's a union of a line out of a plane with a planar, like singular cubic curve. So the singular cubic curve is the conic union a line. So the reason I want to mention this is a common example of what I said previously. So this is definition of W3, the third wall, and then we had a description of the corresponding curve. So remember that was described by this diagram star. So in this case, diagram star reads like this. So when you, the curves Q by W3 satisfy the sequence, this Serre sequence, this E is a cubic curve. E is a planar cubic curve. Right, E is a planar cubic curve. But what happens indeed, so this wall crossing at W3, it does not remove all of those curves, OY satisfying the sequence, but it only removes part of it. So it removes the curves Y that have this kind of description. So this diagram star tells us this curve should have this description is a line union and a cubic curve. But actually, it only kills a line union some very special cubic curve, and where the cubic curve consists of a conic union a line. You only remove the singular one, not a general smooth cubic. Okay, so this is what I want to say. So we have a common example of this previous criterion. Okay, so maybe let me just briefly say about the very last example to make it complete. So we can also put the following result. I think this was mentioned in Troutman's note, but I think maybe this is not published. But I think we managed to prove this result using wall crossing. So for instance, we fix the class 022, and then we use wall crossing to prove this result that the Gieseker moduli space only has two components. We have two components. So okay, I think my time is up. So let me just briefly go through some key steps. So firstly, we should consider wall crossings for V twisted by 1, as before. And then in this case, we managed to prove that for any Gieseker stable sheaves, when you twist it by 1, it always has a section. So that is the reason we use the class V1. And so for the corresponding curve, so we can compute that the corresponding curve has Hilbert polynomial 3t plus 2. And then here's the description of the Hilbert scheme. There are 3 components, H1, H2, H3. So you see for H1, it parameterizes a planar curve with points. So as I showed before in the third thing result. So this component will be removed. And then the rest 2 components survive the wall crossing. So these are basically the 2 components in the Gieseker moduli. And altogether there are 5 walls. So briefly, this is the wall crossings. So we start with 3 components. So these are the fiber Hilbert scheme. When we cross the first 3 walls, and then one of the component is completely removed. And when we cross the very last wall, so one of the component undergoes a flip. But a general curve, sorry, this component survives, but only we replace a component by some other component, but this component is still there. Right, so the conclusion is this fiber Gieseker moduli has 2 components, called G1 and G2, and they're both saturated. So here saturated, I mean a general pair is saturated. And they correspond to part of H2 and part of H3. Because when I say saturated, I mean a pair corresponds to a curve. So one component corresponds to a general curve in H2, and one component corresponds to curve in H3. So here I said corresponds to curves in part of H2. So part because there's a flip for H2. And so strictly speaking, this one of the components corresponds to curve in H2, but not in the following form. So because W3 kills these kind of curves, so that are a line union in a point with this conic and sorry. So this is a very degenerate case of a twisted cubic, so which is a line and a conic. So here a general curve in H2 has a point, but here the flip kills the curve with a point that is contained in a plane. Okay, so I mean this is a special curve killed by the flip. So the component, the saturated pair, does not correspond to such a curve, but it corresponds to a curve in H2, but it doesn't look like Y or the other curves. Okay, I think that is all I want to show for today. Okay, thank you.
Thank you very much, Dapeng. I'll stop the recording and then we can go for some questions.